Hello there, I Dr. Anuj, and today we are going to discuss about metal hydride complexes. In last lecture we discussed about the metal carbonylates complexes, and we have discussed that when metal carbonylates complexes attract proton, then obtained compound is known as metal hydride complex or carbonyl hydride complexes. Okay, so according to definition, it is metal hydride complexes metal when metal central atom, maybe transition element or main group element, when this metal attached with directly hydrogen atom, this is metal hydrogen bond, that is hydride. And especially when carbonyl number of ligands are available in this complex, then this complex is known as metal carbonyl hydride complexes. Okay, this is metal carbonyl complexes, metal carbonyl hydride complexes, because of hydrogen attachment, directly attachment with metal. Okay, before 1950 this complex was not believing that there is a direct bond between hydrogen and metal, but after that some advanced spectroscopies prove this, that this metal and hydrogen bond is a covalent character bond, and this type complex exists. Okay, so that's why if we take NMR spectra of metal hydride complexes, the peak position of this proton will be located between 0 to 60 ppm. Okay, ppm. And if you take a FTIR spectra, the peak of this bond, the frequency due to this bond will be 1500 to 2200 centimeter inverse, you will find. Okay, so this is FTIR signal approach. FTIR signal may be in this range, and this is 1H NMR signal will be in this range for metal and hydride bond. Okay, why I am telling that it is metal hydride complexes? Okay, because here this H is negative and acting as a ligand, so that's why when H is negative it is hydride ion. Okay, and this is attached with metal, so that's why the obtained complex is known as metal hydride complexes. You can say here that when metal attached with this hydrogen which has one lone pair, and when this hydride, this is hydride ion, right? This is simple hydride ion, this is hydride ion, and when this hydride ion directly attached with metal, then this complex is metal hydride complex. Okay, so that's why this is hydride and is general name. Okay, because of hydride ion coordination, directly coordination with metal, so that's why these are metal hydride complexes. Okay, I have already told you that the NMR peak, proton NMR peak of this bond will be located between 0 to 60 ppm, and FTIR absorption will be located between 1500 to 2200 centimeter inverse. Now another important point is about its acidity and basicity. We will discuss in detail when I will teach about I will talk about its chemical properties. Then I will talk detailed acidity and basicity of metal hydride complexes, but just have a look about its basicity or acidity due to this proton. Okay, so it has been observed that it may act as an acid or it may also act as a base. It depends on the electron density of metal and the type. That means because this hydride may be bridging form, or this is maybe terminal. I will talk in detail in next lecture. Today my purpose just for the synthesis and just introduction of the metal carbonyl hydride complexes. Okay, so after today I will discuss about its chemical properties, physical properties, and some structural parameters. So then we will make a clear conclusion on its basicity, acidity, and bridging, and some other parameters of this. Okay, so we have already discussed that metal hydride complexes are those complexes in which hydride ion directly attached with metal. The obtained complex is known as metal hydride complexes. Now we are going to discuss the synthesis process of metal hydride complexes. Okay, this metal hydride complexes synthesis. First of all, you can prepare metal hydride complexes via simple protonation process, protonation reaction of metal carbonates complexes. So that's why you can say that protonation, you are going to study the synthesis of metal hydride complexes, metal hydrides, right? Metal hydrides. First is protonation of metal carbonylates, as you know, metal carbonates, that is like metal carbonates with negative charge, metal carbonyl complexes with negative charge, known as metal carbonates complexes. Okay, so you can take an example just like cobalt CO4 1 negative. This is cobalt carbonylate ion, and when you do the reaction in presence of acidic environment S3O1 positive, it will release one proton, and that proton will attracted by negative charge which is available on cobalt. So that's why this proton will be directly attached with cobalt, and your new complexes will be metal hydride complexes. This is your metal hydride complex. Okay, similarly you can take another example of iron complex or chromium complex also. You can say you can take an example like chromium CO45, and this is 2 negative. Okay, when it reacts with H3O1 positive hydronium ion, it will release one positive ion and one negative ion from this, because it is 2 negative ions. So one negative charge will be utilized to attract one proton, and your complex will be HCr and CO whole 5 and 1 negative. Okay, similarly in next step you can utilize this negative charge also, and your complex, your product will be H2CrCO whole 5. Okay, one thing is here that always remember this proton will be attached with cobalt, because this negative charge is not on complex. It just this negative charge is on metal, because this ligand is neutral ligand. So that's why this negative charge is on cobalt, and cobalt is acting as a nucleophile, and this nucleophile attacking on electrophile which is H1 positive. So that's why after action, the connectivity of electrophile and nucleophile will define the product formation. Okay, so that's why this is nucleophile, this is electrophile, and in product they will connect directly to each other. So that's why the obtained complex is metal hydride complexes. Okay, similarly here you can also take some example of iron type like Kumar reagent. This is Kumar reagent FeCO4, and this is 2 negative. This is Kumar reagent. Okay, and when you react with H1 positive source, you can say H1 positive source, you can take acidic solution just like hydronium ion, and it will release one positive ion, and it one negative charge will also attack on this, so it will form HFeCO whole 4 and one negative, and it can again react with H1 positive and form H2FeCO whole 4. Your complex will be H2. Your complex will be, I am writing here, your complex will be H2Fe and CO whole 4. You know, this is the first complex, first metal hydride complex which formed in lab. Okay, this was the first metal hydride complex is discovered. Okay, so this is the synthesis method via protonation of metal carbonylates ion or complexes. Okay, you can say also this is acidification of metal carbonates. Okay, this is acidification process. Okay, this is also known as acidification of metal carbonates or protonation of metal carbonates. You can prepare some metal hydride complexes. Okay, now we are going to discuss another method by the action of metal hydride on metal carbonyl complexes. Okay, so you can say that another method is action of metal carbonyls. Okay, with hydride donor, any hydride donor. So I am just writing simple hydride donor. Okay, so this is your repetition method name, action of metal hydride with hydride donor. Okay, sorry, action of metal carbonyls with metal hydride donor. You know, metal hydride donor, just like NaBH4 or lithium aluminium hydride. These are metal hydride types complex, B2H6 also. So when this complex break, then it will release Na1 positive, and this is BH4 1 negative, and this species then can act as a nucleophile and donate some hydrides, one hydride element. Just like here, you can you can understand this unit in this fashion. This is H and this is BH3, and this H is negative and act as a nucleophile, that is hydride ion. So this hydride can be donated to other species. Okay, similarly here, this is also can donate hydride donor in similar fashion. So these are the hydride donor species, and when these species react with metal carbonyls, then metal hydride complexes will be formed. Okay, let's take some example. If we take some example, CO whole 4 Fe and Cu. This is very simple example, and now we are going to react with metal hydride complexes. So I am writing this CO in simple fashion, in bonding fashion, and you know the chemistry of this carbonyl is like this. Okay, because metal carbonyl complexes, carbonyl ligand attached with metal via single bond and one partially pi bond character. And okay, and here is also the bond order will be less than 3 but greater than 2. So I am representing this carbonyl bonding in this fashion. Okay, you can say, you can write also in easy fashion like this, FeCO whole 5, but I represent FeCO whole 5 in this fashion to understand the mechanism of action of metal hydride donor species. Okay, and when it reacts with NaBH4, I have already told you that it will release BH4 1 negative. Okay, and this unit is H1 negative BH3 type. Okay, and when this negative will attack on here, okay, this unit will H, this bond will attack here and this bond will attack here, okay. So because the electronegativity of iron is greater as compared to oxygen here because of electron vacancy, electron deficiency in metal atom, in central metal Fe atom, because of pi acceptor, 4 pi acceptor ligand are attaching here, so that's why they also are withdrawing some electron density from iron. So the electron withdrawing, electron flow direction in this complex is from here to here, okay, from carbon to here, okay. So that's why when this this bond, BH bond, act as a nucleophile and attack on this carbon, then this bond will be break here. So that's why you are putting one negative charge on Fe, because this is also a neutral again and this is also a neutral again. So that's why you can put this negative charge out of sphere, coordination sphere, okay. So you can represent this product like this, CO whole 4, and this is Fe, and this is Fe, and this is C, this is double bond O, and this is H, and one negative charge, okay. Or you can also put this negative charge here, because doesn't matter. One thing is here, this negative charge is on Fe, because CO remains ligands are neutral ligands, okay. Now what happened next step? Now, because this hydrogen is very active hydrogen, because it is alpha hydrogen, and always alpha hydrogen is less stable, and in this case this bond will break and shift it toward iron, and this bond will break and shift it toward carbon, and it release one CO molecule, this has break from Fe, so that's why this is simply removed, and now your complex is ready. This is CO4 Fe and H. This is metal hydride complex, and one negative charge is here, okay. And now you can take one negative charge if your reaction is going in presence of in presence of acidic environment, then it can attract one proton from the solvent like H3O1 positive, and it will attack one positive ion, and it will form a CO4FeH2 type complex, okay. This is your final product. So you can make metal hydride complexes via this reaction, where metal carbonyls react with reducing agents such as sodium borohydride, lithium aluminum hydride, or you can say that these are hydride donor, and this hydride will act as a nucleophile, and it can attack on the electrophilic carbon of carbonyl ligand, and it can make some metal carbonyl hydride types complexes, okay. Another method is direct method, where metal can easily combine with carbonyl and hydrogen in a single step, and they can form metal carbonyl hydride complexes, okay. And also this method is like oxidative cleavage of metal bonds, okay. If you have multinuclear metal carbonyl complexes, just like binuclear metal carbonyl complexes, trinuclear metal carbonyl complexes, tetranuclear metal carbonyl complexes, in that case the bond between metal and metal can be easily cleavage via oxidative pathway, okay. Oxidative pathway, that means you are going to break metal bond, and you are giving two protons to each metal, okay, and you can form metal hydride types complexes. Let's discuss that synthesis method, okay. Okay, it is third method by oxidative cleavage, oxidative cleavage by oxidative cleavage of metal bond, or by direct method. It is also known as direct method. Okay, if you have, suppose, an example you can take, CO whole 5 Mn and MnCO whole 5. This is your complex. This is Mn2CO whole 10 metal carbonyl complex, and it is binuclear metal complex. Why it is binuclear? Because of two metals are available here. And now you can break Mn bond, that is metal bond, okay, via oxidative cleavage. Oxidative means you are giving to proton to here, okay, and just like you are making this reaction with H2 in some suitable pressure and temperature condition, just like here 200 bar pressure and 150 degree centigrade, okay, and this hydrogen will break in this fashion, it will also break. So this I mean, you can say here this bond is here and this bond is here, and your complex will be HMnCO whole 5 2 I mean one neutral molecule, and both are similar, so this complex will be like this. This is metal hydride complexes, okay. Another thing is that this complex can also react with a halogen, and then you can replace that halogen with any hydride donor species, and you can make simply metal carbonyl complexes like this. If this complex is similar complexes, I am making another reaction in such way. If you are reacting with this complex with X2, then X will also break in this fashion, similar fashion. This is X and this is X, okay. This will be here and this will be here, so you will make X MnCO whole 5. This is your halide type complexes, okay. And now you can react with any reducing agent, just like lithium, aluminium hydride, and then you can replace this H via hydride ion, okay, and you can make a new product. It is HMn and CO whole 5. This is your metal hydride complex, okay. So this is oxidative cleavage of metal bond, and you can make many metal hydride complexes using binuclear, trinuclear, tetranuclear metal hydride complexes. You can make a lot of complexes from this method. Just you need to understand the mechanism. What is the mechanism of MM bond cleavage? I represent here, just like you can follow the mechanism and you can make a lot of complexes from this, okay. You can design any reaction on the basis of this, okay. Now we are going to discuss the direct method. I told you that in direct method you can react with metal with I am writing here, this is direct method, okay. You can react with just like cobalt. I am taking an example of cobalt react with 4CO in presence of half molecule of H2, and you can make directly H cobalt CO whole 4 complex. This is metal carbonyl hydride complex of cobalt, and you can prepare this. This reaction is more specific for cobalt and nickel. Mostly this reaction pathway can be followed only by cobalt and nickel specifically and easy fashion. So you can make some nickel and cobalt metal hydride complexes from this pathway, okay. So this is all about the synthesis of metal carbonyl hydrides or metal hydrides complexes. I have already told you that this proton can be identified on the basis of proton NMR spectroscopy, and you will find the peak between 0 to 60 ppm for this proton, and you can also identify this NH bond on the basis of FTIR spectroscopy. You will find the absorption band between 1500 to 2200 centimeter inverse. Then you can identify that this is metal hydride bond available here. Okay. In next lecture, we will discuss some critical properties of metal hydride complexes, just like acidity, basicity, size, and etc. All lot of factors inside of metal hydride complexes we will discuss in next lecture. Okay. So today it's enough for today. Okay. Thank you very much. Thank you.